All right, I'm back. So we're going to continue. This has been boiling now for more than 10 minutes. So it should be pretty well thermally equilibrated. So let's take a look at what's next here. So boil gently for 10 minutes. The flash should be surrounded by as much. Record the temperature of the boiling water with your thermometer. Okay, so we're going to record the temperature next. And so the bubbles, yeah, I used the boiling chips, but it's still getting big bubbles in there. I probably should use some more boiling chips in there. Okay. So we're going to record the temperature. I'm going to take a picture of it here. And then we'll get the measurement. And so I'm not going to let it rest on the bottom, and I'm not going to let it touch any glass. I'm just going to suspend it in the water. And let's measure temperature. Let me see if that came out good. Not to read. Yeah. Okay, thanks. Okay, so let's take a measurement. Now, you know, these are not high precision, high accuracy thermometers. These thermometers are just mass produced. And so the reading could be off, you know. This is the 100 line. Obviously, this reading is off, you know. This is 100. The next line here, you can't read it, is 10, 20, 30. So this is 100. It's between 102 and 103. You see that? And so what are you going to call that? 102 point what? $102.8, okay. Anybody else? The meniscus isn't very good on this one, unfortunately. Well, it's not totally clear cut. And so there could be some. I would probably go off the most dense part of there. I wouldn't say 0.8 maybe. I'd say like 0.6 or 0.7, you know, like 102.7. Let's see. So you got 102.8, 102.6. Anybody else? Point six. 0.6. All right, so it looks like the most votes are 102.6. So we're going to go with 102.6. So that's what we're going to do here. It says temperature of boiling water, except I'm not going to mark up this. The report sheet I need to keep clean. I had written on this because this is for something else. Okay, we should date the previous entries. I forgot to date these ones. You know, this was a different date. Today's date is 7/30. 7/30/20. That's the date. And so now we're going to go to Charles Law again. This is going to be a new experiment here. So we're just going to collect the data for Charles Law. And so we have T of the boiling water. Boiling H2O, 102.6 degrees C. Okay, T for boiling water. All right, so we got the temperature, recorded the temperature with the thermometer. Okay, but I don't want to let the thermometer sit like this because it can break. So let me remove that and set it on the counter. All right, now it says cooling the air in the flask, measuring the lower temperature and related volume. Loosen the utility clamp from the support rod and cover the end of the glass tubing with your fingertip. Remove the flask from the boiling water bath and submerge the flask with the clamp attached in a sink full of cold water. With the glass tubing directed downward, remove your finger and keep the flask submerged for 5 minutes. At the end of this time, and with the tubing submerged, raise or lower your flask until the water level inside the flask is the same as the water level in the sink. While it is in this position, cover the glass tubing with your finger, remove the flask from the sink and turn it upright. Measure the volume of water in the flask using a graduated cylinder and record the temperature of the water in the sink. Okay, so I don't know if you got all that. Here, I need, Kyle, can you help me with this? Can you stand over there? Stand over on this side. Just hold it. And so here, keep an eye on this so you can see. So move this. See what's going on here. So actually, a lot of water is boiled off. Take a look at the level. I should have replenished it, but this is what we're going to do here. Hold it up a little bit higher. Oh, thanks. Okay, I need to cap this. So this is filled with hot air, but as air cools down, it contracts. And so the reason for capping this here with my finger is so that, cold air can't rush in here as this contracts. Okay, so what I'm going to do is I'm going to cap this here. I have to watch out because one of the most common injuries in lab is burns. And so if I touch any hot metal and cold metal look the same, hot glass and cold glass look the same. And so I got to be careful. And steam burns can be very severe. So I got to watch out for the steam here. I don't want to burn. And so if it gets too hot. And so, excuse me. So what I'm going to do is I'm going to loosen the clamp here. I have to be very careful because this is buoyant. And so there's a lot of buoyancy on this. So I'm going to lower the clamp and this thing wants to shoot up here. It really wants to shoot up. And so I'm going to cap it with my finger here and trap it. Now I'm just going to hold this. I'm not going to grab the flask itself. I'm going to hold it with the clamp here. And I have my finger covering this. And so now this is hot air trapped in here. If I were to remove my finger, it's getting cold now and it'll suck in there. Okay, now what I got to do is I'm going to take this over to the sink with my finger on here. I'm never going to let go and then completely submerge this in the cold water. I filled the sink earlier with cold water. Excuse me. So I have to force this down here. Can you get in? Point it down, yeah. And so I force this down. Now it's submerged under the water like this. Okay, now the tip is submerged underwater too, here. My finger's still on that, and the whole thing is submerged underwater. Now if I let go, rather than sucking in cold air, it's going to suck in cold water. But that's not a problem because I can measure how much cold water gets sucked in there. And so I'm going to remove my finger from this and let the cold water get sucked into the flask. And so the cold water is being sucked into the flask because the cold air is going to contract. And then I'm going to leave this underwater for 5 minutes total. So this whole thing is totally underwater right now. And the reason I'm going to leave it underwater is I want to make sure for 5 minutes is I want to make sure it thermally equilibrates there. So it's totally underwater right now. And I'm going to get my thermometer here. I'm going to put the thermometer in the cold water here. So let's see how long it's been. The flask is still a little bit warm. So 20, so probably 226. I'll remove it here. Maybe I'll have my assistant hold it under the water here. Can you hold it under the water? To make sure the top doesn't come out. Thanks. Okay. I have the boiling water bath still going on, so I'm going to shut it off. Problem is this. People don't shut these off. If they don't shut these off, what happens is all the water is boiled off, and you're left with no water in there. Right now, the temperature is not going to get hotter than 102.3. But once all that water is boiled off, then the temperature skyrockets because remember the flame temperature is quite a bit hotter. And so we don't want to leave boiling water baths unattended because then flame will skyrocket the temperature, and that could cause, potentially dangerous reactions if you have a reaction going on, or potentially dangerous conditions. And so what I did was I just shut off the water. Now this is a pot of hot water that can cause 3rd degree burns, 2nd to 3rd degree burns. So we got to be very careful here. And so what I'm going to do is I have a ceramic plate here. I'm going to put the water on the plate. Now normally when we grip this, it's going to be very hot. I don't want to touch it. And so normally we have some beaker tongs to grab it. But I don't have my beaker tongs big enough for a 1,500 milliliter flask. So I'm going to do this, just making sure I don't burn myself with the steam, and use this glove for a little bit of insulation. But it's still very heavy and it could slip out of my hands. So I'm just going to let that cool down there. Except we're going to do a trial number 2. So I need the boiling water bath again. So that's what I do when I shut it down. But let me get trial number 2 started here. Now let's see if I have another flask. So while that's cooling, I'm going to start trial 2 with a fresh, dry 500 milliliter Florence flask. I'm going to find a stopper that fits this properly. Now, these things are mass produced, and so what happens is not all of them look the same, and not all of them have the same diameter neck, and so we have to size these individually. And so this one fits properly. I can get a good tight seal with this rubber stopper. Usually, you can twist it on, twist it off to get a tight seal. Okay, I didn't have to take this down because I'm still going to boil more water, but I need to add some water to this. So I'm going to take this over here, and I'm going to add some warm water to this. Lower the boiling time. Oh, I don't have any warm water. Yeah. Pretty cold. Okay, let's see if this will overflow. This is going to overflow. I have too much water in here, so let me take some of the water out. Now let's take a look. Will this overflow? No, that's good. Okay, I'm going to have to get another utility clamp because we have the utility clamp being used for the other flask there. Okay, for the utility clamps, usually if it's too tight, I squeeze this in here and then just undo the wing nut. And so it opens it up. And then I'll just squeeze it back on here like this, and then just tighten the wing nut. Like this. Okay. And then we're going to put this in here. This. As deep as possible, but this is going to interfere here. I want to leave a little bit of room because I don't want water splattering out of the beaker here. A little bit of room. This is going to be for trial 2. There we go. And then let me relight the burner here. Okay, that's good. All right, now I'm going to have my assistant help me here for a minute. Okay, this is very tricky, this next part here. So it's been equilibrating for enough time in the sink. Or actually, maybe I should do this. Can you hold the camera? Go ahead and let it go. Okay, let's try to get it to the camera so you can see it. Flask, okay. Now, there's a little bit of water in here. And so what we need to do is, I need to hold this inverted like this. And so it's upside down. Now, when I pull this out, then take a look at the water level in the flask. The water level in the flask is way up here, and the water level in the sink is down here. This works like a manometer. And so the gas that's pushing on the sink is the atmosphere. The gas that's pushing down inside the flask is the trapped air. Now, is the atmosphere and the trapped air at the same pressure? The answer is no. Right now, the atmosphere weighs more. The atmosphere weighs more than the trapped air here because you can see the difference in the water level. If the trapped air in here has the same pressure as the atmosphere, then the water level should be the same. We can adjust that a little bit. Here, I can lower it. Okay, if I push this in, it's probably hard to see, but the water level now inside the flask is way down here. It's way down here. And so in that case, what's happening is that actually, let's leave that here. I'm going to leave this here like that. Okay, can you point it to the, sure. You over here. Watch out, it's jerking there. Okay, so this is the situation that we have. This is exactly like a manometer. Make sure, let's see. So the flask is upside down right now. Let's like that. So we have two water levels. We have the water level outside. If we look at the water level outside, then what's pushing down or weighing down on the water level outside is the barometric pressure or the atmospheric pressure. We'll call it a piece of atmosphere. What's pushing down on the inside is the trapped air in here. And so we had different scenarios when the two levels are not the same. It's open down here, you know, because of the tube. And so water can flow in and out of the flask. It's open in the tube. So right now, the air pressure here is greater than the gas pressure inside here. So this is the pressure of the gas. And so we have the pressure of the atmosphere is greater than the pressure of the gas. Okay. Let's go on to the next scenario here. Can you move it to the side over here? Thanks. Well, the next scenario is this. If I were to push down the flask, if I were to try to submerge the flask more, it forces water in here. As it forces water in here, it compresses the gas. So I'm going to push the flask down more. And so I do that. And I'll push it down until I get the two levels to line up or to match. And so here, the water level inside the flask matches the water level outside the flask. And so as I push this down, it forces more water in here, which compresses the gas and makes the gas higher pressure. And so what that's going to result in is that the atmospheric pressure outside is equal to the pressure of the gas inside. And so here they're equal. The pressure of the atmosphere is equal to the pressure of the gas. And so what I have to do is I have to adjust the height of this, right? The way I adjust the height of this is by forcing it down or pulling it up. If I were to force it down more, that would force more water in there. If it forces more water in there, this is what's going to happen next. Unfortunately, I got to erase it. So if I push it down too far, it's going to force more water inside the flask. And so if I push it down too far, now the end of this has to be submerged because we don't want air coming back in here. Actually, this is supposed to be pushing down too far. If I push it down too far, it forces more water in here and compresses the gas. You know, it can only compress it to a certain amount. And so in this particular scenario, we have a situation where the pressure of the gas inside here weighs more than the pressure of the atmosphere outside here. And so in this case, the pressure of the gas is greater than the pressure of the atmosphere. And that's not what we want, actually. And so what we have to do is we have to play with the level here so that we can get the pressures to match. Okay, so maybe my assistant's going to do that here. I'll hold the camera so you can watch. So my assistant can, okay, making sure that the stem never goes into air. Can you adjust the height of that? Stand over on this, or this side maybe. And you gotta get your eye level down so you can see it better. But lift it up or lower it down until the two levels are equal. When you think the two levels are equal, then what you're going to do is you're going to seal the bottom of the glass tube there. In this case, it's the bottom because it's submerged. Wait, don't seal it there because look, the liquid is too high. What you got to do, you can tilt it. To help you better do it, you can tilt it as well. You see, this is too high. This is too high. The liquid level's out. This is too low. The liquid level's in. So what you got to do here, let me hold the camera. Right? What you got to do is you got to get it just right, you know, to where the two liquid levels are equal. And so tilt it to the side a little bit, but don't let this come out. Now leave it open until you get the right. Don't seal the stem yet. You got to get it to the right height and then seal the stem so no water can enter and no water can exit. And that's just the right amount of water that should be in there. And so get the two heights level. Now you got to get down there and look. Look at my fingers on the outside liquid level. It's too low. Up, 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 up. Okay, now it's a little bit too high. There. Now seal the end. Okay, now flip it right side up and take it out of the sink. Okay. Okay, now you can let go because no water is going to come in or out. Okay, so this is the right amount of water, in other words, for the gas that was in there. Okay, now with this clamp on here, it's going to make it difficult. Actually, for this, you don't need the glove. Can you undo the clamp off there? Hold the flask and then unscrew this. A little more. Okay, there. Okay, now what we need to do is we need to measure the volume of the cold water that entered into the flask. And so I need a graduated cylinder to do that. But before I do that, let's measure the temperature of the water. And so we're going to measure the temperature of the water here. Can you hold this for a second? I'm going to take a picture of this paper. Okay, so I can measure the temperature of the water in here. It's probably fine. Go ahead and do that. I'm going to tilt this. I got to make sure the bulb is submerged. Go ahead and measure the temperature of the water. Or I can measure the temperature of the water in the bath. Maybe it might be easier to measure it in the bath. It's kind of hard to measure it here. And we're going to just assume that, you know, this has been sitting there for more than 5 minutes. So we're just going to assume that the bath temperature is the same as the temperature of the water inside the flask. So,
Your hand is over the microphone. We can't hear you.
okay. Back up a little bit. Okay, can you hear me now?
Yeah.
I'm not sure. Is it this one that's saying? How's the audio now? Can you hear me?
Yes, we can hear you.
All right. All right, let's go ahead and take a look at that temperature measurement here. All right. What would you say that is? It's a little bit blurry, but you can kind of see it. It's paper towel on the side. It's right on the 20 line. So if it's right on the 20, these are measured, the next line is 21, 22, all the way up to 30 here. And so it goes by 1 degree Celsius. And so if it's right on the 20, yeah, we call it 20.0, exactly. And so the temperature of the cold water is 20.0. All right, let's continue on. Now our boiling water bath appears to be boiling. You can see the bubbles forming on the bottom surface of the beaker. The bubbles should be forming on the boiling chips. Those boiling chips aren't very good. There are better boiling chips out there. These aren't the best I've used. Here, let me back it up. Let me see if you could see it. The bubbles should be forming on those little stones that are in there, but they really aren't. They're forming on the bottom surface of the beaker. And so those aren't very good boiling chips. That's probably why I was still getting big bubbles that were forming. Okay, so let's see what we got to do next. So we did C. Let's go on to D. Actually, we didn't measure the volume of the water in the flask using a graduated cylinder. Okay, now I got to measure the volume of the water in the flask using a graduated cylinder, but my graduated cylinder is a bit too small, and I'd have to fill it 2 times, maybe, or 3 times. I have a 50 milliliter graduated cylinder, and that one that's a 500 milliliter. That one looks like it's going to be more than 50 milliliters. And so I probably want to use a bigger graduated cylinder for this. And so hold on, I'm going to get a bigger graduated cylinder from the stock room. Just 1 minute. I'll be right back. Just keep an eye on that. Let's mark the time. So it's a good boil. It's 2:42. You're going to measure it. Okay, so I got 100 milliliter. Hopefully 100 milliliter will do it. Let's see. Can you guys hear me all right?
Yes.
Thanks.
Yes.
So let's go for the 100 here. Actually, can you pour it? Or here, actually, let me pour it in this one. You'll do the next one. Okay, just point it at this. So I need to pour all this water into the grad cylinder just to measure that volume. Okay, fortunately, it was under 100. If it was over 100, I'd have to do it twice or get a bigger grad cylinder. And so in this case, I'm going to take a picture of this measurement. Now for water, we measure it at the bottom of the meniscus. The meniscus is going to be con K. Let me see if that came out okay. Yeah, I think that came out okay. So let's take a look at this measurement here. So this line is 90 here. Let's see if I can get better. So we got 90, it's not focusing. Let me see something. Getting a lot of reflection off the screen. Okay, so it looks like it's between 92 and 93. So what would you call it? I'd say 90 is this long line down here. So this is the 90 mark here. 91, 92, 93. So it's between 92 and 93. 92.6, 92.7, 92.5 would be midway. And so you're going to measure from the bottom of the meniscus, 92.7. All right, we're going to go with 92.7. That sounds good. Let's just do that. 92.7. So let's record that in our book. And so we're going to start recording some of the measurements here. So we had the temperature of the boiling water, 102.6. We had the temperature of the cold water, which was 20.0 degrees C. We have the volume of the cold water that came in. The volume of the cold water is 92 point, let's go with 92.7 milliliters. All right. Next, fill the flask with tap water and insert the stopper until its lower end is exactly where it was originally. Be sure that the glass tubing is filled with water. Remove the stopper and let the water in the tubing drain into the flask. Determine the volume of water by pouring it into a 500 milliliter graduated cylinder, and the total volume of the flask will be more than the value stamped on its neck. And then repeat the entire process one more time. Okay, so I was in the stockroom. I grabbed a 100 milliliter, but now I need to grab a 500 milliliter flask. I was looking for a 500 milliliter flask, but give me a minute. I'll be back with 500. So we'll watch the water boiling here. Well, I can't find the 500 milliliter garage cylinders. Those are expensive, so they probably locked them up in some secret location. So what we're going to do is we're going to have to do multiple measurements. Multiple measurements, you'll see what I mean. Okay, so hold this. So even though this flask is reading 500 milliliters, is it really 500 milliliters? No, about 500 milliliters is usually to the bottom of the neck or somewhere around here. This is actually holding more. So what we want to do is we want to figure out what the volume of hot air was, you know, when we cap this with our finger. And so the volume of the hot air is going to be the entire container plus the stem here, because that's where we capped it. And so what I need to do is I need to fill this up with cold water. So I filled this up, and then I'm going to put the stopper on here. When I put the stopper on here, I want to make sure that I fill up the stem with water too. This one's not quite all the way full. And so what I'm going to do is I'm going to just get my wash bottle and add a little bit more water to completely top it off. And so now it's completely topped off. Here. Put some paper towel here. Still. Okay, then I'm going to remove the stopper here and let it drain inside the flap with a little bit of excess there. Okay. And so this is the total volume of hot air that I had in there originally. And then I'm going to use this grad cylinder to measure that. But this grad cylinder should be dry. And so I'm going to tap it here. It should be dry because I don't want to measure the water that's in here originally. To dry a grad cylinder is you take a paper towel and you make it into a rigid rod. The way you make it into a rigid rod is you keep holding it like this to make a rigid rod like that. And then we can try to dry down to the bottom of the grad cylinder here. Otherwise, the water that's already in here is going to add to the volume of the water. I don't want that. And so, dry it as best we can. You know, but there's a trade-off. Obviously, I can spend a half an hour drying this, but you know, if there's a tiny bit of water, it's going to lead to a little bit of error. And so we want to get the bulk of it out of there. But if there's some tiny droplets in there, then maybe just leave those because it would just take too much time to get that out. And so this is pretty dry now. And so what I'm going to do is I'm going to pour this in, but I don't want to overshoot the 100, so I'm going to go below 100. I'll have to do this 5 or 6 times. And so I'm going to go below 100, and then we're going to add up the volumes. So let me record the first. See if that came out okay. No, it didn't. Trash this. Try that again. I have to hold it perpendicular. If I hold it like this, it's going to take too high of a reading. If I hold it like this, it's going to take too low of a reading. You want it straight perpendicular. And so in that case, I didn't get it quite perpendicular because I could see it from the top. Better. Let's see if that got it. Okay, that looks better. There. All right, can I have that for a second? All right, so let's take a look at this first measurement here. All right, here's 90, here's 95. So it's between 95 and 96 It depends on where you measure it. Now, it's kind of hard because maybe I should black out that meniscus, but it looks like it's right on the top of the 95 line. And so what would you call that? What would you call that? 95.1? Do you guys agree? 95.2? All right. Maybe I need to black out the meniscus here. Can you hold up a second? Black out the meniscus. And make that a little easier to read. And so I need some black object. Let me use a stapler here. Black out the meniscus. Okay. Let's see if that worked. Yeah, it worked, but it came out a little bit blurry. Lines came out blurry. Let me take one more shot of that. All right. Thank you. Hard to see, huh? This camera is not so. This is a 720p camera. You got 1080. All right, can you guys see that? Now, this is the 95 line here. 91, 92, 93, 94. Actually, the 95 line is here. It really depends on the angle that I hold this. See, I gotta be very careful, but now take a look at the meniscus. The meniscus is totally blacked out because I put the stapler. You can see the black stapler. I put it just below the meniscus so that the meniscus is completely blacked out. And so this is 90, 91, 92, 93, 94. Oops. You can see the stapler behind it. Actually, it's right above the 95 line. Let me go 91, 92, 93, 94, 95. So it's 95.1 now. What do you call it? 95 point.
Who's that Pokemon? Andrew. Andrew. You got you.
I would say it's a little bit higher than 95.1 because, let me point. Here. I think I gotta mute. 1 second.
You did check.
I'll do something really quick. Okay. Now I'm not thinking it's 95.1 because of this. Okay, this black, the bottom of the black line is a meniscus right there. The bottom of this black. So where my pen is right now. And then it's hard to see because I have the stapler behind it, but this is the 95. It's probably because of the contrast. It's so hard to see. Let me see if I can blow it up some more. It's not focusing very well. Here. Hold that for a second. Okay, thank you. So I blew it up more. Yeah, it's washed out. You guys can't see it. The top, this is the 95 line here. And then there's a gap. This is the 96 line. And so it's looking like a 95.2. 95.5 is here, so it could actually be a 95.3. Maybe you could see it. So let's go with the 95.3. Okay, so we got to add the rest. All right, so what I'm going to do is I'm going to dump this. And then, unfortunately, I got to dry it. And making a rod. Get the bulk of the water out of there, and then remeasure it. So this, or here, I'll do it. Okay, I got to go below the 100 here. I got to take 6 because I can't find that grad cylinder, unfortunately. So I'm turning into quite a big time sink from measuring this. But nobody's around, so I can't ask him. There are a lot of cabinets. Let's see if you can see this. So at least the bottom of the meniscus is a bit clearer. Right there. It's right underneath this line here. So this is 90, 91, 92, 93, 94, 95, 96. So it's between 95 and 96. So this is the 95 line. Try to tilt it so you can see it. This is a 95 line, that's a 96. So this is looking like a 95 point. You got 95.9. It's just, it's probably hard for you to see the lines just because of the resolution of the camera. I get a 95.8. You know, 0.9 should be a little bit closer to that line because the 95 lines here, you can't see it though. That's the problem. Is the camera there's light reflecting off the screen of my camera, so you can't see it. So 95 line is where my pen is. 96 line is there. So I get a 95.8. Can you mark that? And so what are the volumes so far we have? We have a 95.8. What was the volume on the last one that we got? $95.3, thanks. 95.3. Each time we take a measurement, there's uncertainty. So this is a bad way of doing it. To measure this volume in 5 or 6 measurements means, you know, we're getting, you know, 5 or 6 times the measurement uncertainty versus one measurement. If we just did a one measurement, then, you know, there's less uncertainty. So unfortunately, It's taking some time here to do. So again, I got to dry this off. I'll just get the bulk of the water off here. That. Okay, and then just try to speed things up here. Let me show you this measurement here. So this is 90, 91, 92, 93, 94. So it's between 94 and 95. And so this meniscus didn't get clearly as delineated, but it's a little bit below halfway. So I'd say 94.3. It's kind of hard to read, but 94.3 or 94.4. Let's go with a 94.3 here. I'm going to speed it up a little bit because take 6 measurements of this. Let's count that. Okay, I'm going to dry the bulk of the water out. If I had a bigger grad cylinder, my life would be much easier right now. Another measurement. All right, let me just tell you what the measurements are. 94.9 is the next one. 94.9. Again, try to get the bulk of the excess water out of there. Do this one time. Okay, let me just tell you again what this one comes out to. This is 95.4. So the next one came out 95.4. Dump that. Okay, let's try this. This will be the last one, fortunately. Okay. Okay, the last one came out to 75.5. 75.5 milliliters. So what I'm going to do now is I'm going to add them all up. I'm going to add them all up to get the total volume. So it's 95.3 plus 95.8 plus 94.3 plus 94.9 plus 95.4 plus 75.5. 551.2 milliliters. 551.2 milliliters was the total volume of the flask, including the tip there. Okay. We're not going to go 2.0. 2.0 is too much precision. We should just leave it at 2.2 because this one doesn't read, the grad cylinder doesn't read that precisely. Excuse me, the grad cylinder is only going to read to the nearest 10. So let's take a look at the calculation here. Well, actually, let's collect the data for this one here, and then we'll look at the calculation. Okay. Okay. I'll have my assistant. Yes.
It's break time.
Oh, is it break time? All right.
Yeah.
All right. It's break time, so we'll let this one keep boiling. But you know, the volume of the water has gone down quite a lot. And so to prevent this from going down too far, I'm going to refill it with some water here. And so I'll do that before going on break. Just refill it with water to top it off again. It's too small. And then we'll let this boil over the break. All right, so let's take a 15-minute break and then we'll start up again. I'm going to pause the recording. I'll see you guys back in 15. Okay, so this has been boiling. So what we're going to do is going to remove it. So this side. You got to go back and behind. Okay, so go ahead and what you'll do is that you got to cap it, remember? There, and then unscrew it there from the clamp. And this is, it's buoyant, it's submerged, so it's going to come up like a balloon. So, you know, be careful when you loosen this. Okay, and then grab it by the clamp and lift it out. Okay, keep it capped and then bring it over the sink. Okay. And then submerge the whole thing. And make sure you put the nozzle under the water. Yeah, good. Like that. Okay, and then we have to let it sit under the water for, how long was it? Let's see, it's got to sit under the water for 5 minutes. And so we'll take a look. Wait, yeah. 5 minutes should be adequate. All right. You could let go of you don't have to hold the nozzle. You could let the cold water in, but it has to be submerged for a good 5 minutes. So unfortunately, you got to sit there for 5 minutes. Let's record the time. So in about 4 more minutes. Okay, while that's being submerged, let's record the temperature of the boiling water. So here, I'll hold that. You record the temperature. Okay. Okay, go ahead and record the temperature. So, let's see. Okay, what you can do for the temperature is it doesn't take long for the thermometer to calibrate, but it's going to take a little bit of time. Go ahead and read it. What do you read for the reading?
Can't see.
All right. Just 1 minute. When you record the temperature, you should hold it perpendicular like this, and then make sure it's perpendicular to your eye, and then just try to read it there. See if you can read that. Get it? Okay. Take a picture. Okay.
99.5.
All right, hold it towards me. Make sure the bulb is submerged. And then let me get the angle right on here. And okay, let's see if this photo came out. Just leave it in there in case. All right, do you guys see that? What do you call that? Again, the top of the meniscus is not so clear. You know, so I would agree with all those readings, but we're just going to go from the densest blue part. And so to me, it looks slightly below halfway. And so when I look at that, I'm looking at like a 99.4 maybe 99.3. But I can easily see how you could have it higher because, you know, this is a mercury thermometer is a lot easier to read because the meniscus is a lot clearer than these alcohol ones. But I would say a 99.4 or 99.3 even, maybe a 99.2, maybe not. Because I'm going off the center of that 94 line to the midway mark. So I'm going to go with a 99.3, maybe 99.3. Okay, this is run 2. And so we collected the data for run 1. And here we're going to do 3 trials. Even though 3 trials, statistically, I spent all that time telling you 3 trials is better. But 3 trials is going to take way too much time. So we're going to just go with 2 trials. And so the temperature of the hot water, I'll just call it hot, is 99.3, let's say. We'll just compromise with that. Whatever you do, you want to be consistent. Well, that's quite a bit different than what we had before here. But it's okay. That's what it's reading right now, 99.3. That's pretty far off. I'd like to see why it's reading so far off. Okay, now this has been sitting in the sink upside down here for at least 5 minutes. And the whole thing should be submerged because we want to get the air inside that flask cold. So can you hold that upside down and then get the liquid levels the same and then cap it with your finger. So what we're doing is we're equalizing the pressures by getting the 2 liquid levels the same. And then, you know, it's going to force water in or force water out, you know, depending if we push it down or pull it up. And so we got to get just the right amount of water where the 2 water levels are equal, inside and outside, and then cap it with a finger. And so here, I'm going to hold my finger on the outside level down a little bit more, or up a little bit, sorry, down. Watch the inside and outside, and then see. Right when they match, go. So go high, go low, and then go back up until it matches. Yeah, that looks good. Cap it. Okay, so that's the right amount of water. Now flip it over. Flip it over. And so now that we got the right amount of water, you can let go of it. Okay, and so let's tap in any water that's trapped there. Okay, now go ahead and undo the stopper. Just twist it, you know, off to the side. Now, fortunately, well, now let's look at how much the volume is. The volume here actually looks more than 100 milliliters. This is a 500 milliliter flask. That's looking more than 100, and I don't want to do dual measurements. So fortunately found the large grad cylinder here. This is a 500 milliliter grad cylinder. Big one. And so go ahead and pour that all in here. That's good. And now I'm going to take a photo of this one to get the measurement. But you can see that, you know, the readings here goes 100 to 150. So it goes in increments of 10 milliliters. So the next line above 100 would be 110, 120, 130, so on. And so this is going to have a lot less precision, but at least we don't have to do it 6 times or whatever. In this case, it'd be 2 times, but 2 times wouldn't have been so bad. Okay, let's go ahead and take a picture of this reading here. Can you hold the camera? Just set that so it doesn't fall, yeah. All right, so I'm going to try to black out the meniscus by holding this black background up there. And get it. All right, so the 100 lines here, and then it goes 110, 120, 130. So it's between 130 and 140. So can you see it here? Right there is completely blacked out. And so when I look at that, it looks like, well, it looks like, what would you say? This is 130, 140. Right there. 137. 137, I'm reading it from the bottom of the black here. The bottom of the black is where the tip of my pen is. It looks like it's below halfway to me. It looks like it's below halfway. Halfway would be 135. Yeah, I'm looking at a 130, maybe a 133. To me, it's looking almost halfway. So I'd say a 134 in this case. And so here I'm going to do 134 milliliters. And so I'll go back over here. The volume of the cold is going to be 134 milliliters. Okay, I have the boiling water bath going on. Can you shut off the gas for the boiling water bath? Thank you. Okay, now the next step is for the data, we need to measure the volume. So can I have you fill that with water? Where's the top? This one? Okay, and take it out. All right, set it over to the side over here. Now we got to make sure it's filled to the tip, which it is in this case, but there's some water that's spilled on the side here. Let's get rid of that water here. All right, now I'm going to dump this water here But drying this is going to be a big pain. You know, this can take too many paper towels and whatnot. And so I'm just going to try to get as much water out of this as possible without breaking it. Okay, now can you fill this? Oh, actually it's not. Look at that, all that air. Do you see all that air? It's not full. Try it again. Okay, just set it on the side. If we need to use the wash bottle, we could add some more water. Okay, let's dry the sides off there. Don't, you know, we want the water there, so we don't want it to come out the top there. Okay, that's good. Now go ahead and remove the stopper. With a twist, and then gently take it off. All right, now dump the water inside the big flat, the grad cylinder. Be careful not to spill any outside. You can grab the cylinder and hold it like this. So you could tilt the grad cylinder. Tilt the grad cylinder more. Did any spill out? No. Oh. All right, now this is a problem. This grad cylinder only measures to 500, and that held more than 500. Obviously, we can't measure it. And so can you pour the excess water? We have to go below 500. Can you pour the excess water back in the flask? Carefully so you don't spill any on the outside, on the ground. You might have to grip it lower to get more leverage. Yeah. So we'll have to do 2 measurements, but 2 measurements is better than 6 measurements that we did before. So anywhere below 500 is good. All right, that's okay, I think. Let's take a look. So that's below the 500 milliliter line, and so we're okay. And so I'm going to take a picture of this now. Let's take a measurement here. Try to black out the meniscus again. Let's see if that worked. No, that worked. Okay, thanks. All right, so let's take a look at this here now. So the 500 is this one. So that's 5, 10, 20, 30, 40, 50, 60, 70, 80. And so it's between 80 and 90. And so this is the 80 line. This is the 90 line. Gosh, it's hard to see. And so it looks like it's below halfway. And so when I look at this, it looks like it's an 83, maybe an 82. Here's 90, here's 80. So I would say like an 82, maybe. And so let's go ahead with that. It's kind of hard to see. And so the volume, this is what we call the volume of the hop, because the hop filled the entire thing. And so we have 582 milliliters plus. Okay, can you dump this and then fill it with the rest? Go ahead and dump it. Okay, and then fill it with the remaining water over there. Wait, we'll just shake this out. Wait. Shake it out because there's some. There. Okay, good. right, so it's a remaining water. So let's go ahead and take another shot of this one here. Okay, this time I'm not going to black out the meniscus. Let's see how it comes out without it blacked out. I mean, the counter's blacking it out a little bit. And so, all right. And so it's about there, the bottom of the meniscus. And so where are we at? Well, this is 50, 60, 70. So we're between 70 and 80. And it looks like it's almost right on the line, at the top of the line. So in other words, this line here is the 70 line there. And this line here is the 80 line. 72, 71, yeah, either of those I'd go with, 71, 72, looks good. 72, anybody else? That. All right, it's looking like it's right on the line. Since I didn't black it out, let's go with the 71, because if I blacked it out more, it would be just a little bit lower. And so 71, so 582 plus 71, we'll just type that in. 582 plus 71 gives us a total volume of 653. So this flask is, like I said, each of these Florence flasks are different. Actually, these are even different manufacturers, but they're different, slightly different. They aren't exactly the same. In fact, even two flasks from the same manufacturer aren't even the same, because they're all glass blown. And so they come out a little different. All right, so let's look back at the data sheet and see if we collected everything we need to. Okay, there's one more thing. We need to measure the temperature of the cold water. And so the temperature of the sink probably changed a little bit during this time. So we need to remeasure the temperature of the sink. So let me go do that now. The thermometer's been sitting there this whole time. So let's go ahead and take a picture. Let's go back over here. The temperature did change a little bit. What do you call that? All right, I'll do it in just a second. Yeah, it's the meniscus. Now you can see the curve. Well, actually, if this camera was a little bit better resolution, you can see the curve. It looks like it's right above the 19. So 19.1, 19.2, both of those sound good. Looks like most people said 19.1, so we could go with that. But, it's off the center of that. And so 19.2 is fine as well. But whatever you do, just try to be as consistent as possible. And so the temperature, we'll just write that. The temperature of the cold is 19 point. This looks like most people wrote 19.1. We'll go with 19.1. All right, the hot was 99.3. The cold was 19.1. The volume of the cold is 134. we don't have the same precision as before because we're using that big grad cylinder, which is less precise. And the volume of the hot was 653. Again, not the same precision as before because of the big grad cylinder is a little less precise. All right, now let's take a look and see, did we collect all the data required for the experiment? And our goal is just to collect the data. We'll do the calculations later. If we have time today, we'll do them today. So we got the temperature of the hot water for trial 1 and trial 2, volume of hot air, which is the total volume. We got that. Temperature of the cold water, we got the volume entering the flask. The rest are asterisks. And so these asterisk ones are calculations. We'll do the calculations later. It's nice to do the calculations now in case we have to repeat it, but sometimes we just don't have time to repeat it. And so we're gonna just skip that for right now. Okay.
Hey, Professor, will you be
We're
uploading?
done with the data collection for Charles Law. I'm sorry, did somebody say something?
Yeah, will you be uploading a picture of all the stuff? Because it's sometimes a little hard to see.
Yeah, I'll upload the pictures of the measurements so you can compare them to your notes.
All right, thank you so much.
Okay, yeah, no problem. Yeah, it's hard to see with this camera. This camera, I should have gotten the 1080. Like I said, it would have been a lot easier to see with the 1080 camera, probably. This is 720. But webcams are hard to come by right now. Okay, now what we're going to do is we're going to go back to the next one, the common chemical reaction. So let me, can you hold it? Okay, so let me get rid of this stuff. And so I'm going to dump this, make sure it's cool enough to touch. Let's dump this here. And so now there are a lot of hard water deposits. The hard water deposits are difficult to clean because those aren't water soluble. And so normally what we'll use is a little bit of acid, and the acid should clean it, but I don't have any acid right here to clean it now. And then we have the wire gauze. The wire gauze, you got to be watch out for hot metal because if you touch it, I mean, it looks cold, but it isn't. Unfortunately, this is already cool. I don't feel any heat radiating off this. Rings are common. People get rings, burns. Can you hold it down a little bit? They get burnt with their thumb all the time and fingers by gripping a hot ring. Hot rings look the same as a cold ring. This is still radiating heat, so I don't want to touch it. So for rings, I usually grab it by the clamp here, and do it that way. The clamp is going to be cool enough to the touch. And then we could return the equipment back to the back there. We might need this though, and so I do need the burner, and I need the burner to do the magnesium. Now, I found some magnesium, fortunately. This magnesium is not the cleanest magnesium. When you look at the color of the magnesium, it looks gray to black or dark gray. And that's due to oxidation and corrosion on the surface, but that's all right. I have to be careful because magnesium is going to generate magnesium oxide, and it can appear as a smoke. And that smoke can set off the fire alarm. And I don't want to set off the fire alarm because I'm the, there's nobody else on campus. So what I'm going to do is I'm going to do this in the hood. And so I'm going to disconnect the power, and then we're going to move over to the hood, and then we're going to do this in the hood. Just go by the hood now. The hood is good because do you hear that suction? Here.
Can't hear you.
All right. Can you hear me now?
Yes.
Okay. When I lift this up, here, let me move this over. Do you hear that?
Yes.
Okay. What that is there's a lot of suction in the hood. And that's good because it's going to suck all the smoke out of the hood. Yeah, good things. We have a burner in the hood, and so there's the gas over here. Well, I'm going to turn on the gas first. Like the burner, this burner has a very weak flame. A little bit better, but it's hard to do a burner inside the hood because the air is sucking it in. Get some tone on there. It's probably pretty hard to see the flame, but you probably can't see the flame very well, but there's a flame there. I got 3 strips of magnesium I'm going to burn here just to make it a little bit brighter. You're not supposed to look at this directly because it does produce some UV light. UV can damage your eyes, but you're looking at it through the computer, so it's probably all right. But for me, I'm not going to look at it directly. Kyle, you should see it. Okay, I'm going to ignite the magnesium. Let me turn off the lights so we can see it a little bit better. And I'm doing this in the hood so I don't set off the fire alarm. Okay. Let me shut off the gas there. Okay, let me flip on the lights. Okay, so you can see what happened here. This white stuff is the magnesium oxide. This is unburnt magnesium, so it didn't all burn. Still have some unreacted magnesium, but what we're looking at is the magnesium oxide, which is ceramic. You know, it's like a salt. It's not going to conduct electricity like magnesium would. And so let's go back and let's take a look at the. Let's take a look at the product on the wash lot. Okay. Yeah, sorry about that. We got disconnected. Or actually, computer just shut off. Let's take a look at the product here in detail. So this is the magnesium oxide here. That's unburnt magnesium metal over here. And you guys saw the brilliant white light that comes. Magnesium used to be used in old-fashioned light flash bulbs, you know, for cameras, photography. Okay, what are we going to do with this? Well, we're going to test the magnesium oxide. Magnesium oxide is what we call base. You know, it's not a very strong base because it's insoluble, but it is a base. And so we're going to take a look at a reaction of magnesium oxide. And so let's go back over here. Okay, so we catch the ash from the above reaction on the watch glass, crush the ash on the watch glass with a stirring rod, add a few drops of distilled water and stir. Test the resulting mixture with red and blue litmus paper, then add a drop of phenolphthalein. Okay, we have a red and blue litmus paper in the back. Can you grab a bottle of red and blue? Well, we get some litmus paper. I'm going to clean up a little bit. All right, can you crush the white stuff with this? Grab the wash bottle right there. Okay, first crush up the white powder with this. Just the white powder. Hold the watch glass steady. Try to zoom in. And so one reason for crushing it up into a fine powder is to get it to react a little faster. Now, magnesium oxide is not soluble in water, but even though it's not soluble in water, a tiny bit will dissolve. Okay, that's adequate. Now, spray a little bit of water in there. We don't have distilled water, we just have deionized water. Okay. And you can see it doesn't really dissolve. Here, let me get rid of the magnesium strips. Let's move that out. Okay, crush that up with the water. You can move that, hold the watch glass steady, and then crush it like back and forth like this. Yeah, like that. You try to crush up the crystals. And it forms a suspension, so it doesn't really dissolve, but that's okay, a tiny bit will dissolve. Now we're gonna test it with litmus. When we test with litmus, we don't put the litmus directly in there. What we do is we set the litmus on the side here. And so, okay, you can stop crushing it. Now, grab a piece of blue litmus, and can you put it on the watch glass? You have a 2, it doesn't matter. Okay, and then put a piece of red litmus. So the blue litmus is kind of purple blue color. What litmus paper is, it's a piece of paper that's pH sensitive. And so it has a dye in there that changes color with pH. Now get the stir rod, get a drop of that suspension and put it on the blue litmus paper and let's see what happens. Okay, that's fine. Get another drop and put it on the red litmus paper. Okay, put a little bit more on the red litmus paper and let's see what happens. Okay, a little bit more. Okay, crush it up more. And then put it on the red. Okay, now when we look at it carefully, notice that the blue litmus paper, nothing happened, it's still blue. However, the red litmus paper is turning blue. Do you see that? Okay, now what blue stands for is blue stands for base. And so bases turn blue. So if it's already blue, then blue goes to blue. Then nothing happens. So nothing happened to the blue. But the red is going to turn blue. And so bases turn blue. And so what that means is magnesium oxide is basic. We got a little bit of magnesium oxide in the water. And we know that oxide's a good base, but magnesium oxide is not that great of a base because it's so insoluble in water. And so that's what we have here. Okay, then we're going to add a drop of phenolphthalein. Now, phenolphthalein is colorless in acid, but pink in base. And so, let's see. Let me grab the phenolphthalein. And so this phenolphthalein is colorless here. So this is it's neutral to acid is colorless. If it's base, then it should turn pink. And so phenolphthalein is used as a test for base because it's going to turn pink. So can you unscrew the top and then put a drop in? In there. Okay, take a look at what happened to the color. Can you see the color? Okay, put another drop in there. And then let's tap this down. So it turned pink. This again confirms that magnesium oxide is basic. Okay, well, what we need to do now is we need to make sure that we have our bases are very damaging to the eyes. And so we got to make sure that, you know, we have eye protection on. You don't want to get bases in your eyes. It can cause severe eye damage. And so you should be wearing safety goggles. We use these visor goggles here. Visor goggles provide splash protection. You want a good seal, you know, on the bottom here to prevent splashes from coming up and getting in your eyes. You know, regular glasses, they don't provide the seal on the bottom. And so regular glasses aren't okay. You need splash protection goggles like these. Fortunately, magnesium oxide is a pretty weak base, so I'm not too worried about this. Of course, we work with stronger bases than that. All right. So next, we did that. Let's see what kind of observations. So we should write some observations here. What types of observations do we do? Magnesium is burned in air. What did you see? You saw bright white light, you know, in the flame. The equation we had written on the board. The magnesium metal turned into white ash, or, you know, the product of that was that white powder, the white solid. It wasn't powdered until we crushed it. Okay, the ash from above is mixed with water and tested with indicators. And so the observations, did you write your observations there? So we crushed it, mixed it with water, and then tested it. We tested it with litmus. Blue stayed blue, red turned blue. That was the litmus here. Blue stayed blue, red turned blue. And then phenolphthalein. Phenolphthalein went from colorless to this color. Pink is what people call it. What are the equations for that? Okay, so let's go ahead and write the equations here on the board. So get this bigger here. I can't really see this very well, unfortunately. All right, let's see. I can't see the chat either. Just record your observations. Don't worry about what number it is. Just record the observation. And so the next observation is going to be what we're doing with that white solid. This was the product that we generated from that last reaction, magnesium oxide. When we react it with water, H2O liquid, this is one, it's either Lewis acid base there's a Lewis acid base reaction in this sense here. Let me see if I can get it. Can you hold this for? Let's see. Can't I see this? It's not. Can't get this full screen for some reason. I'll just kind of point it up here and see if that works. Okay. Now, the way we do this Lewis acid base, since we've been talking about Lewis structure, what is the Lewis structure for magnesium oxide? So let me do that over here. So here, I'll point it this way. I'll try to talk loud. Lewis structure is going to look like this. It's going to be magnesium ions, which will write like that. And then oxide ions. Oxide ions are going to have a full octet. Oxide itself is a powerful base, but it's locked in this lattice. And this is a very strong lattice. This is a very strong lattice because it's +2 and -2. So this lattice has a very high melting point. Not only that, it's insoluble in water. It's insoluble in water because the lattice doesn't want to break apart. It's got very strong ionic bonds. And so we're going to just extend this lattice in 3 dimensions. Now, for each oxide, we want to surround it with as many magnesiums as possible. And for each magnesium, we want to surround it with as many oxides as possible. So because of this strong lattice, it doesn't dissolve in water. So even with crushing of the crystals, barely any of it dissolves. Now, it's insoluble, but insoluble doesn't mean 100% insoluble. Insoluble means very, very little dissolve. So with crushing, we got some of these ions to go in water, but we don't even have to do that because what's going to happen here is a water molecule is going to come along and react. Now, this oxide is a powerful base, and it really wants to react with hydrogens. You know? And so what can happen here is this. A water molecule comes and collides with the oxide ion here. When that happens, it pushes, these electrons into the hydrogen. And it pushes these electrons into the hydrogen. There's an orbital here. This is an S, so we call it sp3 sigma bond. But we haven't talked about hybrid orbitals, so I'm going to leave it like that. And what happens is this oxygen takes the proton, the hydrogen, leaves the electrons behind. So if this oxygen here in oxide takes that hydrogen, what does it form? And so what it's going to form here. It's going to form this. And so it's taking a proton, and therefore the charge is going to go from -2 to -1. And we call this hydroxide. Now, if water loses that proton, what's left behind? Well, if water loses that proton, what we're going to be left behind with is this, a hydroxide. And then we have a magnesium here. Now the magnesium, in order for the charge to balance, we need 2 hydroxides for every oxide that we lose. And so what's going to happen with this hydroxide is this hydroxide is going to come in here and bind into the crystal lattice. Because for every oxide we lose, we need to replace it with 2 hydroxides. And so in essence, what we're doing here is we're going, let's go back over here. We're going from magnesium oxide and water to magnesium hydroxide. Now, magnesium hydroxide is also insoluble, and it's a white solid. So we're replacing one white solid with another white solid. Now, magnesium oxide is a stronger base, even though it's a weak base than magnesium hydroxide, milk of magnesium. And so this is the kind of thing we made. We just made some milk of magnesium. And so there are 2 ways of thinking about this reaction. One way is Lewis acid base. In Lewis acid base reactions, the bases are electron pair donors. The acids are electron pair acceptors. So this oxide donated this lone pair to form a bond right here. And water accepted that. So that was the acid there. Or you could think of this as a Bronsted acid-base reaction where water is the acid, it donates a proton to the base oxide. And so we could think of this as both a Lewis. This would be the way we visualize it as a Lewis acid-base reaction. And the way we visualize it as a Bronsted is it's donating a proton. As a proton donor, then it's Bronsted. And so it's the same reaction, just 2 different ways of trying to visualize that reaction. All right. So that's what we have for that. Let's take a look at the next one. The next one, we need calcium oxide is mixed with water and tested with indicators. Oh, that's good, thank you. So let's grab some calcium oxide here next. All right, unfortunately the calcium oxide went missing. And so we're going to skip calcium oxide, but essentially it's the same reaction as we just saw. Magnesium and calcium are in the same family. So everything we just did, you could replace with calcium instead of magnesium, and it's the same thing. Okay, carbon is burned in air. Okay, this one, there's no charcoal on our card, so we don't have any charcoal. And we don't have any pure oxygen, unfortunately, either. So I was going to burn it in air, which is 20% oxygen or 21% oxygen, versus pure oxygen, which would be closer to 100%. So we don't have those. But anyway, this is going to form hopefully CO2 rather than CO. So it's just carbon solid plus O2 yields CO2. This one we do have. And so let's give this one a try. Hydrochloric acid is placed near ammonia. And so let's try that and see what happens here. You see the hydrochloric acid? The hydrochloric acid and ammonia we'll do after the next break. Let's see what time it is. 4:22. All right, it's break time. So let's go ahead and we're going to take a break, and I'm going to track down some more of the chemicals. They're missing off the cart. The cart was supposed to be set up for this experiment, but it's not quite set up. Okay, so we'll take a break now. It's let's say 4:23, so 4:38 or so. Let's meet back here about 4:40 or 4:38 to 4:40. Okay, I'll see you then. Bye. I'm going to pause the recording. Can you hold it up there again? So I missed it on the recording, but the demo was we're taking hydrochloric acid and ammonia and then letting it evaporate. So some HCl gas is going to vaporize, while hydrogen chloride gas, some ammonia is going to vaporize. And these two gases can react to form a solid. That solid creates tiny crystals, and those tiny crystals look like white smoke. And these are old solutions, so they've gone flat, you know. But maybe you can see the smoke. Okay. Hopefully you saw the smoke there. All right, next we're going to look at copper 2 sulfate. For every formula of copper 2 sulfate, there's 5 water molecules trapped in the crystal. And we have this nice blue color here. And so what we're going to do is we're going to heat it up. When we heat it up, we have two methods of heating things like that. One, we could use an evaporating dish like this, porcelain, or two, we can use a, this is called a crucible. I'm going to use the evaporating dish here, so it's a little easier to see. And so I need to set this up. Can you go over here? Let's take a look at this. Move this chat out of the way. Here. Okay, so again, I'm going to heat it. But in this case, I could heat this directly if I have one more tool. Or I could heat it indirectly. I could heat it indirectly with the wire gauze. This disperses the heat. Or I could heat it directly on this. I'll just heat it indirectly on the wire gauze. I could heat it directly with something called a clay triangle. And let me show you what a clay triangle looks like. This is a clay triangle here. So if I want to heat the ceramic directly, I'll put this here and then set that on the clay triangle like that. Then I can heat it directly. Heating directly, you got to watch out, especially with hydrates, because hydrates can pop like popcorn. You know, the water is trapped in there, like in popcorn. There's water trapped in the seed of popcorn, and that can cause it to pop. And so this could pop like popcorn, potentially. And so can you take a look inside there? So let's get some crystals of the copper 2 sulfate pentahydrate. It looks dry, totally looks dry here. They don't look wet, but they don't look totally dehydrated either. And so I got my crystals here. And when we use a Bunsen burner to heat directly, we have to be very careful. And that is, when we heat things directly, we want to hold the Bunsen burner in our hand. And the Bunsen burners are made to be able to be handheld. And so that's what I'm going to do here. I'm going to hold it because I don't want it to, I mean, if it's going to pop like popcorn, then I want to let it pop slowly or not at all. And so what I'm going to do is I'm just going to hold the burner in my hand and then just gently move the flame along the base. Can you hold it down so let's see? And then you can hold it up again. Okay, let me crank up the flame a little bit. Okay, now let's take a look at what's happening with the crystals. All right, I don't know if you could see it, but can you see steam coming off? Okay, this is not really popping like popcorn, which is good. Okay, you want to hold this, Bernard? Can you come around this way? Okay, hold the burner and just move it along the base. Put your goggles on. Okay. Just move it along the base. Let me try to get this in focus here. Just keep moving it. Okay, what I'm going to do is I'm going to just stir this up a little bit here. Kind of move it in circular motion. Oh, it's too loose. All right, here, let me do that. Tighten them. If things start to get out of control, I can move the heat away rapidly, point it out over here if things start to get out of control. So what I do is I carefully watch this to make sure it's not getting out of control, and then just continue heating. And so I'm always quick to move the heat away. Well, that's not 100% dehydrated, but we'll just go with that. Probably good enough right now. Oops, I went. Okay. Let's see. So let's compare the colors here. It's hard to see because it's all. So I'm going to put these crystals on a watch glass. So I'm going to grip this on the side here. And then I'm just going to pour the copper 2 sulfate in here. There's still some steam coming off there. It's just water, steam. Dangerous gas there. This is very hot crucible. All right, so we can make a comparison between the hydrate on the right, and this is called anhydrous. So that's copper 2 sulfate anhydrous. The only difference between these two is I just heated up to dry off the water. So I totally dehydrated the crystals here. That's it. Okay, the crystals aren't changing, basically. It's just dehydrated. I can rehydrate it. Watch what happens if I just get a little bit of water right there. You see that? These crystals are very hot. I don't want to add too much water because copper 2 sulfate is soluble in water, but you can see here. So rehydrated, we get the blue color back. And so it's the anhydrous form versus the hydrated form. So they want a reaction for that. Let's do the reaction later. Let's collect the data now. What we're going to do is we're just going to do the observations, make sure we get down all the observations, and then we're going to write the equations for it. So the observations were the anhydrous or the dehydrated form was a light, very light blue color, almost white, It is a pretty white color. Actually, it's white. Take a look at the powder. Do you see the powder? Compare the, except the light reflection off there. It's hard to see. The powder at the top, which is white. So it went to almost a white color. Okay, when we do, hold this, see? Okay, do you take a look over there? When I was scraping it, I have some powder that's spilled out. Whenever you spill some solid onto the counter, you want to clean it up. And so I'm going to get some wet paper towel here. And I'm just going to wipe up the spills here. So, there we go. Probably got on my power cord too here. Let me wipe off the power cord. There we go. Okay, let's take a look at the next. That's that's not really a chemical process. That's more of a physical process, dehydration. Let's look at the next reaction. It's going to be copper 2 carbonate. One second. This is copper 2 carbonate here. It's a light green color. Compare the two. Okay, I'm going to do some dehydration of the copper 2 carbonate. This is actually this is a mixture of copper 2 carbonate and copper hydroxide, copper 2 hydroxide. So this crucible up here is still very hot. Can you point to the crucible up here? And so I don't touch this with my fingers. I'm going to grab it with some clamps. I'll set it on the ceramic plate here. Let it cool down. Let's get rid of that glow. Let's get rid of some of this garbage with match heads and stuff. Those. Garbage. All right, now the copper 2 carbonate, though, we're going to decompose. I have the full apparatus for that. Let's skip that reaction for right now. We're going to come back to it because I got to find some additional equipment that's missing off the card here. And so we're going to go to C, which is single replacement type of reaction. And so we're going to do some zinc is added to copper 2 sulfate solution. And so let me get some zinc metal, and then we're going to add that to copper 2 sulfate solution. Put this back. This is copper 2 sulfate solution. So if I took these crystals here, can you point to the crystals? If I took those crystals there and dissolved it in water, this is the color of the solution. It's like a blue solution, blue-green solution here. This is zinc metal. This is zinc metal in chunks. And zinc is a great reducing agent. Zinc is often used in batteries as a reducing agent. Batteries, it's inexpensive and it's a good reducer. And so I'm going to add some copper 2 sulfate to zinc. And so let me get some zinc metal here. Zinc metal is not too dangerous. You know, I could touch this stuff without worrying. It's like, you know, aluminum or something like that. Let me get some pieces of zinc here. Like that. And let's see what happens when we add some copper 2 sulfate to that. Okay, now the copper 2 sulfate's in this gigantic bottle. Can you zoom out? In this gigantic bottle. And so we don't like to pour from the original source because that's our stock solution. And so rather than pouring from the stock solution, we like to pour from a transfer beaker. And so let me get a transfer beaker here. I'm going to do one here. So I'm going to get a small beaker here. We're going to use this as the transfer solution. When we pour from a big bottle, oh, here it is. This is it. When we pour from a big bottle, this is what we want to do. We want to always grab the label. That way, if there are drips, they're on the opposite side of the label. So here, we know always to grab the label. And so drips can go down this side because we don't want to grab the side with the drips because take a look at the top here. Do you see there's some copper 2 sulfate crystals that evaporated? You're going to pan out and then move so you can see it. They're copper 2 crystals. Now this stopper is made like a fin to hold between your fingers. And so what we do is go to twist off. This is called a ground glass joint. And sometimes these get really stuck on there. And so there's certain techniques to do that. Now the stopper, you don't want to set on the counter. Can you zoom out? You don't want to set it on the counter because that's going to contaminate it. Whatever's on the counter, and I put this back on here. Can you zoom out? Is going to contaminate the solution. So I don't want to cross-contaminate. So these stoppers are made to be held with your fingers. So you grab them like this, and then hold it with your finger, and then you can pour like that. And so we're going to pour this here into the transfer beaker. Yeah. And then I'm going to stopper my stock. This is called the stock solution. We don't want to contaminate the stock solution. If I contaminate the transfer beaker, then I've just lost, you know, a couple of 100 milliliters. But if I can, or less, this is less than 100 milliliters. If I contaminate this, then I've lost like a liter. And I don't want to lose a liter of this stuff. And so let me put the stock solution back. Then we're going to use this. We're going to use this for multiple reactions. So I got more than necessary. I'm not going to do this. I'm not going to calculate the stoichiometry of this. I'm just going to mix these two together. Actually, can you mix these two? And so just pour some, pour the copper 2 nitrate into the zinc. Okay, now hold the zinc so people can see. I mean, hold this test tube with like this with your fingers so I can get I can see this bottom part here. Okay, hold on, wait, not yet, not yet. Not yet. Okay, all right, okay, go ahead and pour about this much in there. About, 3 centimeters worth or something. We're not gonna take careful measure. Oh, that's good, that's enough, that's enough. Okay, now let's see what's happening. The zinc. Okay, hold this up like this, or actually, can you hold this? Okay, now when we mix this, sometimes we'll tap it like this. obviously the zinc is not reactive, but take a look at the color change in the zinc. Originally the zinc had this gray color, but if you can see it, it's turning black. You see some of the zinc is turning black. Not all yet. To react. And so sometimes we'll try to mix it up. Some reactions are a little slow, so we let them sit. But this one, do you see how black? Now, there's a black precipitate forming on the surface of the zinc. That black precipitate, we'll just say black precipitate forming on the surface of the zinc. There's still some zinc that's unreacted on this side here. Eventually it'll react. Now, the other thing that's going to happen is the color. The blue color is going to start to fade. So let's let this reaction go. It's a little slow. And so we're going to set this one aside and come back to it. And so I'm going to use a beaker to set this aside here. And let's take a look at it in a few minutes. Okay, let's go to the next reaction here. Copper is added to zinc sulfate solution. Let's see. Copper is added to zinc sulfate. So let me go get some copper here. Let's put the zinc metal back in here. I don't know if we need that again, but I'll set it to the side. All right, the same thing with this. When I have a bottle of the stock solution, zinc sulfate, I want to grab it on the label here. And you see the stopper is a fin stopper like this. I'll twist it to break the seal of the ground glass joint here. You can see all the white, I don't know if you could see the white crust. That's solid zinc sulfate. You know, that's from spills. And those spills, water evaporates and leaves zinc sulfate. Yeah. Zinc sulfate is not terribly toxic. Now, how do you know how bad chemicals are? Well, how bad chemicals are, you look up the SDS or the MSDS. The SDS is the safety data sheet. The MSDS is the material safety data sheet. And it'll give you some idea about how toxic some of these are. Obviously, you want to handle everything with care and respect. But, you know. So the zinc sulfate, yeah, it's toxic. I don't want to eat this stuff, but if I spill a little bit, I'm not too worried about it. And so this stopper is meant to be held with the hand, not to be set down on the dirty counter. It's not, you don't lay it like this, you don't put it down like this, you hold it. I'm just going to get a little bit of zinc sulfate this time. We don't want to waste too much chemical either. And so the stock solution I'll put away. All right. Now we're going to get some copper metal and put it in the test tube and do the reaction. Can you get some copper metal? Do you want me to tighten those? Okay, get like a sheet of copper metal, a big sheet of copper metal. You can find it. Okay, hold it up for the camera. All right, so that's what the copper metal looks like, is fresh copper metal. It's pretty lustrous. You know, it looks pretty good. Just don't move. I'll move. The camera can just, okay. All right, go ahead and set the jar down. And then hold the test tube. Okay, and then put the copper in the test tube. Okay. All right, then we're going to pour the zinc sulfate in there. Okay, now hold it so I can see the bottom. Just a couple of fingers. Just use a couple of fingers. Three fingers. Okay. Okay, and then go ahead and pour that in there. Let's see what happens. So what we can do, well, why don't you tap it like we were doing before, just to try to mix it. doesn't look like much is happening. It doesn't mean that there's no reaction necessarily. We look for heat. So I'm feeling this for heat. I don't feel any heat or cold. And so it looks like no visible reaction. You could try adding a little bit more zinc sulfate and see. Okay, that's good. No. Well, maybe it's a slow reaction. So let's go ahead and put it in the beaker over here and let it sit. Now we have 2 test tubes in there. And so we should label it. There are 2 ways of labeling test tubes. One, we could use this green tape. So grab a couple of strips of green tape and then put it on the test tubes. And then the other test tube also. We don't really need much, but it's all right. All right, and then label the blue one C1, and label the other one C2. All right, with a Sharpie pen, you could label. Okay, take that one out again. Just label on the glass directly, C1, right on the glass. Okay, let me take a look. And so with a Sharpie, you can just write straight on the glass. If you don't have a Sharpie, you use these green labels here. We're doing that. Well, we have a Sharpie, so we're not going to use the green labels. We'll just write right on the glass. Okay, go ahead and put that back on. Well, let's take a look at this one. Now, I don't see any zinc. Well, maybe a little bit of zinc. You can see a little bit of zinc that's not reacted. So let's shake this up a little bit here. Let's continue to react. Okay, let's move on. All right, the next reaction we're going to do is we're going to add copper is added to silver nitrate. Now, silver ions are good oxidizer, you know, good medium strength oxidizer. Actually, no, why don't you do that? You get a test tube. Okay, so go ahead and put a sheet of copper metal in there. All right, 1 second. Silver nitrate is more hazardous. Silver is a heavy metal. And so it's a good idea to wear gloves when you use silver nitrate, because in case you spill some. What happens with silver nitrate is it stains things black, and it'll stain your skin black, basically, when it forms these. So, good idea to wear gloves. This. Okay, so let me get a transfer beaker. So I got this beaker here, it's already labeled. So grab it on the label side here. This stopper is totally different. Do you see this stopper is flat on the top? This stopper is meant to be set upside down. Can you get this? Upside down. That way it doesn't contaminate the ground glass joint. Okay, and then we'll just pour some silver nitrate in here. Silver nitrate's a CCS, clear colorless solution. Let's oxidize something. It's an oxidizer, that's one of its properties. And so I'm gonna get some paper towel. Let's see if we can oxidize some paper towel. Okay, we'll let that sit for a while. You probably can't see it much, but I'll let it sit for a little bit. We'll come back to it. All right, can you hold it? All right, can you put some silver nitrate into the copper? Okay, move it up so we can see it. Let me see. Hold it like there, right there. Okay, wait. Okay. Okay, go ahead and pour the silver nitrate, which is CCS. Let's watch it as it hits the copper. Okay, that's enough. Yeah. Set that aside. Nothing's happening. Something's wrong with our silver nitrate. We should have seen this reaction happens pretty instantaneously. So I'm going to get a fresh silver nitrate. There's something bad about this silver nitrate. It's not working. But anyway, let's label this. Can you label the glass? C3. You don't have to use the green. You could just write it right on the glass if you want. Nothing's happening to the paper either. It's telling me something's wrong. So I'll get some fresh silver nitrate out of the stockroom and see. I think we're gonna need another beaker. Let me grab another beaker. Set it over to the side. Set it aside over here. It doesn't get knocked. Okay, we're going to come back to that one and take a look and see if something happens. Oh, wait, maybe something's happening. Maybe it's not as bad as I thought. Do you see that mold type stuff growing on there? Let's see. Yeah, something's happening there. Can you grab the ball of copper? No, just bring the ball. So that's what it used to look like, the copper, but now it's got a fuzz growing on there. It was sluggish reaction, probably because there's an oxide coating on there. But now there's a black-gray fuzz, white fuzz growing on there. So let's come back to this one. And we'll take some observations. Actually, let's take a look at the zinc. Take a look at that. That was the zinc one. Here. This is the copper with the zinc nitrate. Nothing seems to be happening here still. But definitely the other two seem to be something happening. Okay, let's move on to the next one. Copper is added to hydrochloric acid. Okay, so let's try that. Unfortunately, my hydrochloric acid is not the greatest as far as strength goes. You know what? But I think I got some. Let me check something here. I ran out of big test tubes. This is my last one. Can you put another sheet of copper in there? Okay, can you put some hydrochloric acid? All right, just put in a few squirts of hydrochloric. This is the 6M hydrochloric acid. Put a few squirts, but before we do that, let me take a look at the copper again. Okay, so it's pretty shiny. Go ahead. Here, okay, ready, go. You're gonna have to get more. Here, actually, just pour it in. You can pour it in from the bottle. Okay, that's good. Look this way. It looks, you know what it looks like? It looks like it's getting shinier. So let's test this out here. Okay, can you label that one? Label that one. It should be labeled C4. Okay, so it looks pretty shiny. We can put it in the beaker there. We'll come back to it. I have a new penny here. I wish I had an older penny. But can you see the difference in luster? This one is kind of oxidized. This one's a lot shinier. This is pretty new. It's a new penny and an old penny, older penny. It's not a really old penny. Now, the copper is going to get shinier because the acid, hydrochloric acid, will attack the oxide coating. So if it's copper 1 oxide or copper 2 oxide, we can do it. So can you squirt some hydrochloric acid on the center penny first? Okay, that's enough. I wish this camera were better. Okay, now let's move that aside. Okay, now go ahead and squirt some hydrochloric acid on the center penny now. This is the older penny. Okay. Okay, a little more. Okay. So I'm gonna rinse these off. Can you hold this? I'm gonna rinse the hydrochloric acid off. And then I'm gonna dump this. Now I'm gonna dry off the pennies. What? Can you tell which one's the new penny and which one's the old penny? Take a look. In there. All right, let's try that. Can you tell which one was the old one and which one was the new one? Maybe you can. Still a little bit more lustrous. I probably should have added a little bit more hydrochloric acid. It's all right. Basically, this is the old one here. It's a lot shinier now because the acid will eat up the oxide coating, but the acid doesn't eat up the copper metal itself, so the copper metal is still there. All right, so when we look at the copper with the hydrochloric acid, it's shinier, but the copper metal itself, let's see, copper metal itself is not being attacked. You know? Okay, let's move on. Zinc is added to hydrochloric acid. What we're going to do is we're going to add a hydrochloric acid to zinc. I don't want to do it the other way. Okay. So can you get some zinc in here? Put the zinc in this. We're going to do this in a little test tube here. All right, now squirt some hydrochloric acid in there. Here. Let me see if I can get it to focus. A few more. Okay, let's take a look. Do you see what's happening here? Bubbles of gas are forming. It's effervescing. And so the gas that's forming is a CCG. I think it's going to be washed out with the white. Let's go with the black. All right, can you add some more zinc? I mean, some more hydrochloric acid to that? Okay, that's good. All right, now there's a lot of gas. There's a lot of gas forming. It's a CCG. Now, what is that gas? We got to watch out because this could overflow in the test tube and spill hydrochloric acid out. It's like it's about to do that. Here, let me try to go back. So it's a CCG. Now, what is that gas that's forming? So this is what we're going to do here in the next. We're going to test that gas. Okay, and so I'm going to do a simple test for that gas. Can you hold this? I'm going to see, is this gas flammable? And so I have some matches here, and I'm going to check if this gas is flammable. So let me try that. I have to be careful, because if there's too much gas, obviously I can have an explosion. But let's see what happens here. Ready? Actually, let's do it this way. Ready? I don't want to point this at myself or point it at somebody else. Did you hear that? Let me try that again. Okay. Here, let's build up some gas in there. So I'm going to cap this here. So it builds up a little bit of gas. Okay, ready? Listen. Did you hear that? This matches about. Let's do it again. I'm going to cap this, actually, with my thumb and try to trap as much gas in here as possible. And then I'm going to hold this try it again. Oh, look. Let's do it again. All right. You want to do it? Okay, hold this. It's getting hot. This test tube is getting warm. It's not hot. It's getting warm to the touch. It's a very exothermic reaction. A lot of gas is being generated. Still gas is being generated. Look at all the bubbles here. There's still a lot of zinc left over. So we got zinc and we got HCl reacting here. Try one more time. You hear that? That was a little mini explosion. And the gas is hydrogen gas we got going there. Okay, can you label this one? Next reaction we is lead-2 nitrate is mixed with hydrochloric acid. So we always add the acids. That's the general lab safety rules. Double A. Double A stands for add acids. I'm gonna, lead-2 nitrate, it's like silver. You don't want to spill this stuff on yourself. The same thing with lead-2 nitrate. No drinking in lab. Especially with lead. So let me get the lead-2 nitrate. Here's the lead-2 nitrate here. And let me get a small transfer. Well, I'm only going to do one reaction. We don't have that much stock solution left here for the lead-2 nitrate. And so I'm going to add lead-2 nitrate is mixed. Oh, actually, we do two. With hydrochloric and lead-2 nitrate with sodium chromate. And so I'm going to do it in the beakers, a couple of small test tubes here. Okay. So first off, we're going to do lead-2 nitrate with hydrochloric acid. I'll just get a little bit of lead-2 nitrate. I don't want too much. I'm doing it in a small beaker. I mean, small test tube. So let's pour some of this in here. It should be good. It's a CCS. And then I'm going to do the hydrochloric acid, which is also CCS. Now watch it. Watch the bottom of the test tube. Ready? Oops. Just. Okay. That's it. It turned cloudy white. Now that's just a little bit of hydrochloric acid that's spilled on the side. Do you see the cloudy white solid is settling to the bottom? Let's see if you can see it. Maybe zoom out a little bit. It's hard to see. We'll let this settle. It's a really white, cloudy. There, you can see it. Oops. There. You can see the white solid settling to the bottom. It's a white precipitate. Okay, so this one I'll leave here. This is lead. Okay, the next one is we're going to take some lead-2 nitrate. So I'm going to pour it in here. I'm going to use the rest of it. I don't think I'll use any more lead. Yep, the rest of it. And then I'm going to add sodium chromate to this. Sodium chromate, actually, let's go over here, is yellow, and you can see through it. It's a yellow see-through solution, which means it's a clear yellow solution, or CYS. The chromate has this type of stopper. Now, chromate's a strong oxidizer. And so we got to be careful with this stuff. Oops, that's way too much. So it's dangerous stuff. Let's see what happens when I mix these two together. Ready? Watch the bottom of the beaker, or the test tube. I have a yellow, cloudy yellow solution. So that's a yellow precipitate. We see here, yellow PPT. And so let's set this one aside here. These are the two lead ones. We'll come back to the yellow PPT. Yeah, well, okay, we don't need to label it because those are the lead ones. We're going to keep the lead ones separate because lead is quite hazardous health-wise. We'll keep that separate. Okay, the next reaction we have is zinc sulfate. So I'm going to take the sodium chromate back. Let me clean off the counter a little bit. Let's take the lead back into the cart here. Find my zinc sulfate. Oh boy, I'm almost out. The zinc sulfate is just about, this, not much has happened. This is starting to discolor a little bit, but not much. It's pretty weak. My silver nitrate was pretty weak. I don't have much zinc sulfate left, but that's enough. Zinc sulfate and hydrochloric acid. So here's my zinc sulfate. I'm going to transfer it to a test tube. Can you add a hydrochloric acid to that? See if anything happens. Okay, put another squirt. There's some kind of contaminant that got in there, but the black thing floating around is not anything from the reaction. Okay, that's it. That's enough. Okay, tap it to mix it. Okay, feel if there's any heat being given off. Do you feel any heat? All right, no heat being given off. Okay, let's take a look at it again. Okay, doesn't look like much is happening. And so why don't you label it? Label that one D3. D3.
Break time.
Time. Okay, it's time for our next break. So let me pause the recording, and then after the break, let's take a look at the reactions one more time to see what kind of progress the reactions have made, and then we'll do the remaining reactions. There aren't too many remaining reactions here. Okay, so I'm going to stop the recording.